Now, let's get into the molecular reasons why one acid is stronger than another acid. Bond polarity is going to be one of the factors, and bond strength is going to be the other factor. In both cases, it's going to allow the H plus ion to dissociate from the molecule more easily. So within a period, the more polar the bond, now again, be careful because we're going to talk about periods and groups. So remember what a period is. That is the rows going across the periodic table. So within a period, the more polar the bond between the hydrogen atom and the nonmetal to which it's attached, the greater the acid strength. In other words, the greater the polarity of this bond, the greater the acid strength. Well, why is that? Well, we know that when this has when the electronegativities of the two bonded atoms are the same, the bonding pair of electrons is shared between the two equally. So we could say on average that bonding pair of electron is between the two atoms, in this case the hydrogen and the nonmetal. But if this has a higher electronegativity, it's going to draw the bonding electrons closer to it. And when we do that, of course, we create the dipole moment. But now also see that these electrons being farther away from the hydrogen are going to allow the hydrogen by itself, so it's going to be the hydrogen ion, it's going to leave behind its unpaired electron, so it's going to allow the hydrogen ion to escape more freely. So again, the greater the electronegativity of this nonmetal is pulling the bonding electrons away from the hydrogen, allowing this hydrogen to escape more easily. So for example, we have 3 acids. We have, they're all within the same period, right? Oxygen, nitrogen, and fluorine. And so to determine which one of these is the strongest, so we want to go from the weakest to the strongest. So we want to go weakest to strongest. So the strongest is going to have the one with the greatest electronegativity, right? So it's going to be the one with the greatest electronegativity. Now, if we actually looked at the electronegativities, we could see that fluorine has an electronegativity of 4.0. Oxygen has a 3.5 and then nitrogen a 3.0. You don't need to know these actual Pauling values. All you have to do is look at the periodic table and see that fluorine is the most electronegative. And as you move from right to left across the periodic table, we know that the electronegativity is decreased. So it's going to go fluorine, oxygen, nitrogen. Okay. So the one with the highest electronegativity would be the strongest acid, and the one with the lowest electronegativity, in this case nitrogen, would be the weakest acid. So it would be ammonia, water, and hydrofluoric acid. Well, ammonia we actually classify as a base. So it's not really even an acid at all. But if we were considering it to be an acid, it certainly would be the weakest acid there. Okay, and then water is basically neutral, and then our hydrofluoric acid. So again, this is within a period for a binary acid. So within a period for a binary acid, the greater the electronegativity difference, the greater the acid strength. Now within a group, and again, we're talking about binary acids here. So within a group, so that's going down a column in the periodic table, the weaker the bond between the hydrogen atom and the atom to which it's attached, the greater the acid strength. Well, what do we know about bond strength going down a group? Well, we know as we go down a group, the atoms become larger, and the farther away the nuclei, the weaker the bonds, which again means that the hydrogen is going to be able to escape more easily. So here we have two hydrogen acids, so binary acids, so there's just hydrogen and a nonmetal. And again, the bigger the atom becomes, the weaker the bond becomes, and thus the stronger the acid. It's easier for this guy to escape. So if we look and we want to compare these, and we again want to go from weakest to strongest. So this is going to be the weakest bond or the biggest atoms. And again, as we go down the periodic table, we start with fluorine being the smallest, so it would be the strongest acid, chlorine, bromine, and then iodine's at the bottom. So iodine's the biggest, So it's going to be the weakest acid, followed by the hydrobromic acid, followed by the hydrochloric acid, and then finally hydrofluoric acid would be the weakest acid, right? So this is the strongest acid, next to strongest, then this, and then hydrofluoric acid would be the weakest. Okay, so again, the bigger the atom, the stronger the acid. So the weakest would be the hydrofluoric acid, followed by hydrochloric, hydrobromic, and then finally the strongest would be hydroiodic acid. Okay, so those are binary acids. Now let's talk about the oxo acids. Now, I will tell you that these are really simple guidelines, and we're going to see that not only does bond polarity take effect and bond strength, but you have to take both into account. That's why we can only really compare the binary acids within the same group or within the same period. You can't go diagonally across the periodic table and compare binary acids because, again, it is a complex tug of war, basically, between the bond polarity and bond strength that determines the actual strength of a bond. So we can either go across in a period or down in a group, but we can't go diagonally. So an oxo acid, of course, has the acidic proton bound to an oxygen, and that oxygen is bound to the central nonmetal. Now, this central nonmetal might have other OH groups or double bonded oxygens to it, but this is our oxo acid. Okay, so again, this is some nonmetal over here. Okay. Now, the acidic hydrogen is always attached to this electronegative oxygen, which means already it's trying to pull the electrons away from it. Since this has a higher electronegativity than the hydrogen, it's already starting to try to pull the electrons away from it. But it can also be a lot more electronegative, which means it's starting to try to pull the electrons from this oxygen towards it, which means these electrons are going to get pulled even closer to the oxygen. Okay, so again, we already know that that bond is slightly polar, and so the electrons are going to be pulled slightly towards it. But the electronegativity of the central atom is also going to cause those electrons to be pulled even closer yet to the oxygen, and thus making this weaker and weaker bond, allowing this to come off more easily. The more easily this comes off, the greater the acidity of this particular oxo acid. Okay, so if the electronegativity of the central atom Z is large, then the OH bond is going to be relatively polar and the acid strength is going to be greater, just like I said. So here's hypobromous acid, and we can compare that to hypochlorous acid. Well, the chlorine is more electronegative than the bromine, so it's drawing those bonding electrons between the oxygen and hydrogen even further away. So the hypochlorous acid is going to be stronger than the hypobromous acid. Now note that this is different than we just saw with the binary acids. With the binary acids, we found that hydrobromic acid, HBr, was stronger than hydrochloric HCl. That's not the case for the oxo acids. So if we wanted to put these in order, again, all we're going to do is we're going to look at the electronegativities. The higher the electronegativities, the stronger the acid. So fluorine, chlorine, then iodine. So that's in order of decreasing electronegativity. So the weakest then is going to be the one with the lowest electronegativity. So the weakest acid here is going to be the hypoiodous acid, followed by the hypochlorous acid. And then finally, the hypofluorous acid will be the strongest since the fluorine has the greatest electronegativity, weakening the OH bond the greatest. Okay, now we could also look at the number of oxygens that surround an oxo acid. Well, we know that all the oxygens are electronegative. So the greater number of oxygens means it's pulling more and more of that electron density from this bond towards the oxygen, making this bond weaker and weaker, and thus the acid stronger and stronger. So each additional O atom, again, effectively makes the electronegativity of the central atom greater. As a result, again, the hydrogen atom's easier to come off, therefore more acidic. So if we want to look at a series, so notice that all the central atoms in this case are the same. So the weakest will have the fewest number of oxygens, so that's hypochlorous acid. And then as the number of oxygens increase, the acid strength increases. So it's going to go from hypochlorous acid to chlorous acid to chloric acid to perchloric acid. Okay, so again, hypochlorous acid to chlorous acid because we added another oxygen, more electrons are being drawn away, to chloric acid, again, they're more being drawn away. And then finally, we get to the perchloric acid, and it is really drawing the electrons away. Okay. Okay, so any questions on binary acids, oxo acids? Again, different sets of rules for each type. Okay, then let's talk about polyprotic acid. So each successive hydrogen atom of a polyprotic acid becomes more difficult to remove, therefore becomes less acidic. Okay, so again, acid strengths of polyprotic acids decrease with the increasing negative charge, right? The hydrogen ion is positively charged, so it's harder for that positive ion to escape the negative charge of its anion. So we would expect then the acid itself, the original acid, in this case phosphoric acid, to be stronger, because once we lose an H plus, it becomes minus, so it's going to make it harder for the hydrogen ions to escape. So this will be a little bit weaker than the phosphoric acid. And now all of a sudden we lose another H plus, so this becomes 2 minus, and this is the weakest. We've seen this with the Ka values, okay? There was like, I forget exactly what it was, but there was nearly 5 orders of magnitude between these, and then like 12 orders of magnitude when you jump to here. So the Kas were decreasing very, very rapidly and exponentially. Okay, that is it for this chapter. This is number 58, and it just wants to know which of the following pairs display the greater acid strength and explain why. Okay. So let's say Leah, which one of these is going to be the stronger acid? H3PO4 or H2PO4 minus? Phosphoric acid or dihydrogen phosphate?
Oh, a stronger acid.
Yeah, which one's going to be stronger, this one or this one?
H3PO4?
Yep, so this is going to be the stronger acid.
Mm-hmm.
Why?
Because H2PO4, that's an anion. Anion.
Right, so in other words, the higher the negative charge,
yeah,
the weaker the acid.
What about cations? Is that the same?
Well, what acids have cations? We're talking about acid strength here.
Yeah, yeah.
So the cation will always be H plus, so there won't be any cations.
Oh, okay.
Okay.
Yeah.
And we don't have these things for base strength. This is only for acid strength. Bases are much, much more complicated. Okay. Okay, let's see, Eugenie, which one is going to be stronger? Sulfuric acid or selenic acid? So one of the first questions you have to ask yourself, are these binary acids or oxo acids? Because remember, there's different roles for binary acids compared to oxo acids. So what are these, binary or oxo acids?
Can you go over what the oxalic acid is? Wait,
Oxalic acid.
um,
Oxalic acid is actually a carboxylic acid. So again, there's three types of acids. There are binary acids. A binary acid is going to be the H, which is going to be the acidic part, and then a non-metal, which I'll call X. So X in every one of these cases is just going to be a non-metal. So again, you know, phosphorus. So let me get my crease. So the non-metals, of course, right, are all of these guys over here. Okay. Now, how many hydrogens depends on X itself. So, you know, if it's so for example, chlorine has a -1 charge. So there's going to be 1 H pluses. So it'll be HCl. Sulfur, on the other hand, has a 2- charge. Again, another non-metal. So it's going to have 2 H's. Phosphorus, for example, has a -3 charge. So there will be 3 H pluses to give us our neutral acid. So it would have, N would be 3 in that case. So that's what a binary acid is. There's only 2 elements, binary meaning 2 elements. Then we have oxoacids. Oxoacids have the form, we have a non-metal bound to an oxygen, bound to a hydrogen, this being our acidic proton. Now there could be, this thing could be bound to other things as well, or not. It might just have some double bonded oxygens. It might have another double bonded oxygen. It might have just another OH group. It could have a couple more OH groups, like phosphoric acid has an OH group, OH group, OH group, and then a double bonded O. Okay, but these are our oxoacids. We have a central, non-metal, and then the OH is the acidic part, and then it might or might not, usually does, have double bonded oxygens, and then other stuff maybe. Okay, that's an oxoacid. Then we have carboxylic acids. This is just like it's a very specific type of oxoacid. A carboxylic acid has a carbon double bound to an oxygen to an OH. So it's not an alcohol and a ketone. Together, this is a carboxylic acid, where this would be the acidic proton. The R simply represents the rest of that organic molecule. Okay, so this is just the rest of that organic molecule. So, are these oxoacids, binary acids, or carboxylic acids?
would it be binary acids?
Binary means there's only 2 elements. Does this only have 2 elements?
Oh no, oxo acids.
It is going to be an oxoacid. It's going to be this type of acid. So for an oxoacid, since they have different nonmetals as their central atoms, what is going to make them stronger? Which one's going to be stronger, this one or this one? Since we know they're oxoacids.
Do we go by electronegativity?
Absolutely. So which one's more electronegative, sulfur or selenium?
Sulfur is more electronegative.
Right? We know the electronegativity decreases going down the group, so sulfur is more electronegative. So which one then is going to be the stronger acid, sulfuric acid or selenic acid?
Selenic acid is the strongest one.
Nope. The stronger the electronegativity, the stronger the acid. And again, this is for oxoacids. Okay?
Oh wait, yeah, sulfuric acid, I'm sorry.
Yep, so this is going to be the stronger acid. In fact, it's one of our strong acids. So I don't want you to think of that way. I want you to think of this one it's more electronegative than that one. Okay, any questions on that? Okay, so next, let's see, Michael. I have hydroselenic acid and hydrosulfuric acid. Which one's stronger?
Hydrosulfuric.
I'm sorry, the hydrosulfuric?
Yeah.
Not in this case. Is this a binary or oxo acid? Are these binary or oxo acids?
Binary.
They are binary, right? They only contain two elements, hydrogen and another nonmetal. So if these are binary acids, are these in the same group or the same period?
We're right next to each other. So
They in the same group or the same period?
it's a group.
They're in the same group. So now for a binary acid and that are in the same group, which one's going to be stronger?
Is it the one that's more electronegative?
Nope, that's the period. That's the only one that we have a binary acid in the same period. When we have a binary acid in the same group, it's acid strength. Bond strength is related to acid strength. The weaker the bond strength, the stronger the acid. Which one of these, the hydrogen sulfur or hydrogen selenium bond, is going to be weaker?
The sulfuric one.
No, it's going to be the selenium one, right? The bigger the atom gets, they get bigger as we go down in group. The bigger it gets, the farther away the nuclei are, which means the farther away the electrons are from the nuclei. That's the weaker the bond. So the hydrogen selenium bond is going to be weaker, which means it can give off the H a lot easier. So in this case, this guy is going to be the stronger acid. Okay, that just summarizes everything I said. Okay. Does that make sense? Okay. Jada, which one of these are going to be the stronger acid?
The HiO4.
So the per-iodic acid is stronger than the iodic acid. Absolutely. Why?
I was going based off because of the O4 because there's more of it. So there's going to be more of the electrons.
Well, right. So we have two oxo acids. Same central atom. So the electronegativity of the central atoms are going to be the same. So the more these electronegative oxygens that are going to be pulling away right? They're going to be pulling away. So this is a pair of electrons. And the more we can pull those electrons away from the hydrogen, the stronger the acid's going to be. So the more of these electronegative oxygens around here is pulling those electrons closer and closer to this oxygen, making this bond weaker and weaker, and thus a stronger acid. So for an oxo acid with the same central atom, the more oxygen atoms, the stronger the acid. Any questions about that?